In the present video, I will discuss how to solve the linear programming problem by two-phase method. Let's see the example problem. Use two-phase simplex method to solve the following LP problem. Maximize z equal to minus 4x1 minus 3x2 minus 9x3 subject to 2x1 plus 4x2 plus 6x3 greater than or equal to 15, 6x1 plus x2 plus 6x3 greater than or equal to 12, x1, x2, x3 are greater than or equal to 0. In the two-phase method, first phase is eliminate artificial variables in the basis. For this, first step is assign a cost -1 to each artificial variable and cost 0 to the other variables. Second step is write down the auxiliary in which the new objective function is to be maximized. Third step is solve the auxiliary LPP by simplex method until following three cases arise. First one is the maximize z star is less than 0 and at least one artificial variable appears in the optimum basis at positive level and all zj minus cj are greater than or equal to 0. Second case is maximize z star equal to 0 and at least one artificial variable appears in the basis at 0 level and all the zj minus cj is greater than or equal to the 0. Third case is maximize z star equal to 0 and no artificial variable appears in the basis and all the zj minus cj is greater than or equal to the 0. In the case 1, given LPP does not possess any feasible solution, whereas in the cases second case and third case, then I have to go for the phase 2. In phase 2, solve the final simplex table in the phase 1 for the optimal solution. Let's see the solution. First, to convert the general LPP into standard LPP. First constraint having the greater than or equal to inequality. So introduce the surplus variable S1 and artificial variable A1. Similarly, second constraint also having greater than or equal to inequality. So introduce the surplus variable S2 and artificial variable A2. Then constraints becomes 2x1 plus 4x2 plus 6x3 minus S1 plus A1 equal to the 15, and second constraint will become 6x1 plus x2 plus 6x3 minus S2 plus A2 equal to 12, where x1, x2, x3, S1, S2, A1, A2 all are greater than or equal to the 0. Next step is find the initial basic feasible solution. For this, consider the x1, x2, x3, s1, s2 are the 0 and substitute in the equation. Then a1 value is the 15 and a2 value is the 12. Next, start the phase 1 to eliminate the artificial variables. For this, first we have to modify the objective function by assigning a cost -1 to the each artificial variables and assign the cost equal to 0 to the other variables. Then auxiliary LPP will becomes the maximize z star equal to 0x1 plus 0x2 plus 0x3 plus 0s1 plus 0s2 minus a1 minus a2. Here a1, a2 cost coefficients are the -1. Remaining variables cost coefficients is the 0. And constraints are the 2x1 plus 4x2 plus 6x3 minus s1 plus a1 equal to the 15. 6x1 plus x2 plus 6x3 minus s2 plus a2 equal to 12. Next we have to construct the initial simplex table. Here B is the basic variables and A1, A2 are the basic variables and CB is the cost coefficients. Here A1, A2 cost coefficients are the -1 and XB is the initial basic feasible solution. For A1 initial basic feasible solution is the 50 and for A2 it is the 12. And Cj is the cost coefficients for all the variables. Here 0 is the cost coefficient for the x1 variable. Similarly x2 also 0, x3 also 0 and s1 also 0, s2 also 0. But A1 artificial variables A1 and A2 cost coefficients are the -1. And these are the coefficients of the variables. For this observe the constraints. First observe the first constraint. Here 2 is the coefficient of the x1 variable, then have to enter the 2. Next x2 coefficient is the 4, x3 coefficient is the 6 and s1 coefficient is the -1 and here there is no s2, so its coefficient is the 0 and a1 coefficient is the +1. Here there is no a2, then introduce the 0. Similarly, by observing the second constraint equation, x1 coefficient is the 6, x2 coefficient is the 1, x3 coefficient is the 6. Here there is the no s1, so it is the 0 s1, which means s1 coefficient is the 0 and s2 coefficient is the -1 and a1 coefficient 0 and a2 coefficient is the 1. Next, to calculate the Zj minus Cj values and check the basic feasible solution for optimality. Here Zj is the summation of multiplication of Cb and coefficients of the variables. So first to calculate the Zj minus Cj for the first variable, that is the x1. So Z1 minus C1 for the x1 variable equal to the -1 into the 2 plus -1 into 6 minus 0. So it is equal to the -8. Next Z2 minus C2 for the x2 variable, it is equal to the -1 into 4 plus -1 into 1 minus 0. It is the -5. Next Z3 minus C3 for the x3 variable, it is the -1 into 6 plus -1 into 6 minus 0. It is the -12. Next Z4 minus C4 for the S1 variable, it is the -1 into -1 plus -1 into 0 minus 0. It is the 1. Next Z5 minus C5 for the S2 variable, it is the -1 into 0 plus -1 into -1 minus 0. It is the 1. Next Z6 minus C6 for the A1 variable, it is the -1 into 1 plus -1 into 0 minus of -1. It is the 0. Next Z7 minus C7 for the A2 variable, it is the -1 into 0 plus -1 into -1 minus of -1. It is the 0. Here all Zj minus Cj values are the not greater than or equal to 0 and Z1 minus C1, Z2 minus C2 and Z3 minus C3 having the negative values. Then select the most negative value that is the minus 12 for the x3 column. So x3 column is the key column and calling as the incoming vector, and x3 variable enter into the basis. Next, to calculate the minimum ratio of xp divided by coefficient of incoming variables. First we have to look for the a1 variable row, that is the 15 by 6. Here xb value is the 15 and coefficient of incoming variable is the 6. So minimum ratio is the xb by coefficient of incoming variable, that is 15 by 6. Next we have to look for the second row for the a2 variable row. Here xb is the 12 and coefficient of incoming variable value is the 6. Then minimum ratio is the 12 by 6. Here minimum ratio is the 12 by 6 for the a2 variable row. So a2 variable is outgoing vector and a2 variable is the leaves the basis. Next we have to identify the common element in the key row as well as the key column. Here key column is the x3 column and key row is the a2 row. So common element in the key row and the key column is the element 6. So this 6 element we are calling as the key element. Next step is construct a new simplex table by entering the incoming variable. Next, to construct the new simplex table by reference of old simplex table. Here a2 variable is leaving the basis and x3 variable is enter into the basis. So modify the basis by replacing the a2 variable with the x3 variable in the new simplex table, and its CB value is 0. Next, to modify the remaining values by following row operations. First one is the R2 new equal to R2 old divided by key element. Here key element is the 6, and another row operation is the R1 new equal to R1 old minus 6 R2 new. Here R1 old and R2 old are the row 1 and row 2 for the old simplex table, and R1 new and R2 new are the row 1 and row 2 for the new simplex table. So here motivation is A2 is leaving the basis and A2 coefficients are the 0 and 1. Similarly, x3 variable is enter into the basis, so we have to modify its coefficients also 0 and 1 by following row operations. First we have to look for the first row operation, that is R2 new equal to R2 old divided by 6. First we have to write down the R2 old elements, that is 12, 6, 1, 6, 0, minus 1, 0, 1, and divided by 6 will give the R2 new. Then 12 by 6 it is the 2, 6 by 6 1, 1 by 6 1 by 6, 6 by 6 1, 0 by 6 0, minus 1 by 6 minus 1 by 6, 0 by 6 0, 1 by 6 is the 1 by 6. Enter these R2 new values in the second row of the new table. Next we have to look for the another row operation, that is R1 new equal to R1 old minus 6 R2 new. Here R1 old elements are the 15, 2, 4, 6, minus 1, 0, 1, 0. And R2 new elements are the 2, 1, 1 by 6, 1, 0, minus 1 by 6, 0 and 1 by 6. Then we have to multiply with the 6 for the R2 new elements. It is the 2 into 6, 12, 1 into 6, 6, 1 by 6 into 6, 1, 1 into 6, 6, 0 into 6, 0, minus 1 by 6 into 6, minus 1, 0 into 6, 0, 1 by 6 into 6 is the 1. Next we have to do the operation R1 volt minus 6 R2, that is 15 minus 12, it is the 3, 2 minus 6, it is the minus 4, 6 minus 6, sorry, here first 4 minus 1, it is the 3, 6 minus 6, it is the 0, and minus 1, 0, it is the minus 1, and 0 minus of minus 1, it is the 1, 1 minus 0, 1, 0 minus 1, it is the minus 1. Enter these R1 new values in the first row of the new table. So next to calculate the Zj minus Cj values and to check the basic feasible solution for the optimality. First we calculate the Z1 minus C1 for the first variable, that is x1. It is the minus 1 into minus 4 plus 0 into 1 minus 0. This value is the 4. Next to Z2 minus C2 for the x2 variable, that is minus 1 into 3 plus 0 into 1 by 6 minus 0. This value is the minus 3. Next to Z3 minus C3 for the x3 variable, it is minus 1 into 0 plus 0 into 1 minus 0. It is the 0. Next to Z4 minus C4 for the S1 variable, it is minus 1 into minus 1 plus 0 into 0 minus 0. So it is the 1. Next to Z5 minus C5 for the S2 variable, it is the minus 1 into 1 plus 0 into minus 1 by 6 minus 0. This value is the minus 1. Next to Z6 minus C6 for the A2 variable, it is the minus 1 into 1 plus 0 into 0 minus of minus 1. It is the 0. Next to Z7 minus C7 for the A2 variable, it is the minus 1 into minus 1 plus 0 into 1 by 6 minus of minus 1. It is the 2. So here Zj minus Cj values are having the two negative values, that is the Z2 minus C2 and Z5 minus C5. Among these two negative values, most negative value is the minus 3 for the x2 column. So x2 column we are calling as the key column, and this variable x2 variable we are calling as the incoming variable. So x2 variable enter into the basis. Next step is we have to calculate the minimum ratio of xb divided by coefficient of the key column elements. First we have to calculate this minimum ratio for the first row, A1 variable row. Here xb value is the 3 and coefficient value is the 3. So 3 by 3 is the 1. Next we have to calculate the minimum ratio of for the second row, x2 variable row. Here xb value is the 2 and coefficient value is the 1 by 6. Then 2 divided by 1 by 6, it is the 12. So minimum ratio is the 1 for the A1 row. So A1 row we are calling as the outgoing vector and A1 variable we are calling as the outgoing variable. So here A1 variable is leave the basis. Next we have to identify the common element in the key row as well as the key column. Here key row is the A1 row and key column is the x2 column. So among these two, key row and key column, common element is the 3. So 3 is we are calling as the key element. Next we have to construct the new simplex table by entering the incoming variable. Next to construct the new simplex table by reference of old simplex table. Here A1 variable is leaving the basis and x2 variable is enter into the basis. So modify the basis by replacing the A1 with x2 in the new simplex table and its CB value is the 0. Next to modify the remaining values by the following row operations. That is, first row operation is R1 new equal to R1 volt divided by 3. So first to write down the R1 volt elements, that is 3 minus 4, 3, 0, minus 1, 1, 1 and minus 1. So next to do the R1 volt divided by 3. Then these values will become the 3 by 3 is the 1, minus 4 by 3 and 3 by 3 is 1, 0 by 3 0, minus 1 by 3, 1 by 3 and 1 by 3 and minus 1 by 3. So enter these values in the first row of the new table. Next we have to look for the second row operation is R2 new equal to R2 volt minus 1 by 6 into R1 new. So first we have to write down the R2 volt elements, that is 2, 1, 1 by 6, 1, 0, minus 1 by 6, 0 and 1 by 6. So next we have to write down the R1 new elements, that is 1, minus 4 by 3, 1, 0, minus 1 by 3, 1 by 3, 1 by 3 and minus 1 by 3. So next we have to do the 1 by 6 R1 new, that is R1 new divided by 6. It will become the 1 by 6 and minus 4 by 3 divided by 6. It will become the minus 2 by 9 and 1 by 6. It is the 1 by 6, 0 by 6, 0, minus 1 by 3 divided by, so 1 by 6, so divided by 6. It is the minus 1 by 18 and 1 by 3 divided by 6. It is 1 by 18. 1 by 3 divided by 6. It is the 1 by 18. Minus 1 by 3 divided by 6. It is the minus 1 by 18. Then we have to do the R2 volt minus R2 new, that is 2 minus 1 by 6. It is the 11 by 6. 1 minus of minus 2 by 9. It is the 11 by 9. 1 by 6 minus 1 by 6, 0. 1 minus 0, 1. 0 minus of minus 1 by 18. It is 1 by 18. Next to minus 1 by 6 minus of 1 by 18. It will become the minus 2 by 9. Next to 0 minus 1 by 18. It is minus 1 by 18. Next to 1 by 6 minus of minus 1 by 18. It is the 2 by 9. Next to calculate the Zj minus Cj for the new table. So first we have to calculate the Z1 minus C1 for the first variable, that is x1 variable. It is the 0 into 4 by 3 plus 0 into 11 by 3 minus 0. It is the 0. Similarly, Z2 minus C2 is the 0 and Z3 minus C3 also 0. Z4 minus C4 also 0. Z5 minus C5 also 0. And next we have to look for the Z6 minus C6 for the A1 variable. It is the 0 into 1 by 3 plus 0 into minus 1 by 18 minus of minus 1. It is the 1. Similarly, Z7 minus 7 is the 1. So here all the Zj minus Cj values are the positive values. So Zj minus Cj values are the greater than or equal to the. Here all Zj minus Cj values are greater than or equal to 0. Then check the conditions in the phase 1 to eliminate the artificial variables. So here all Zj minus Cj values are greater than or equal to 0 and max Z star, that is multiplication of Cb and Xb equal to 0. Moreover, there is no artificial variables in the basis. So it is satisfying the third condition. Then we have to go for the phase 2. In the phase 2, consider the final simplex table of phase 1. Also consider the actual cost associated with the original variables and delete the artificial variables A1, A2 columns from the table, as these variables are eliminated from the basis in the phase 1. So next we have to modify the Cj values with the original objective function. So here original objective function is the minus 4x1 minus 3x2 minus 9x3 plus 0s1 plus 0s2. Then modify these Cj values with the minus 4, that is the x1 cost coefficient, minus 3 for x2 cost coefficient, minus 9 for the x3 cost coefficient, and 0 for the s1 and s2 cost coefficient. Moreover, we have to change the Cv values. So x2 cost coefficient value is the minus 3 and x3 cost coefficient is the minus 9. Moreover, we have to remove this A1 and A2 columns. Next, we have to solve the simplex table for the optimal solution. Next, to calculate the Zj minus Cj values and check the basic feasible solution for the optimality. First, we have to calculate the Z1 minus C1 for the first variable, that is for the x1 variable. So Z1 minus C1 is the minus 3 into minus 4 by 3 plus minus 9 into 11 by 9 minus of minus 4. This value is the minus 3. And Z2 minus C2 is the minus 3 into 1 plus minus 9 into 0 minus of minus 3. It is the 0. Next, Z3 minus C3 is the minus 3 into 0 plus minus 9 into 1 minus of minus 9. This value is the 0. Next, Z4 minus C4. This value is the minus 3 into minus 1 by 3 plus minus 9 into 1 by 18 minus 0. This value is the 1 by 2. Next, Z5 minus C5. This is the minus 3 into 1 by 3 plus minus 9 into minus 2 by 9 minus 0. This value is the 9. So here observe so except the Z1 minus C1, all Zj minus Cj values are the greater than or equal to 0. Here negative value is for the Z1 minus C1. So Z1 minus C1 is the negative value for the x1 column. So x1 variable is the incoming variable and x1 column we are calling as the key column. Next, to calculate the minimum ratio, that is the xp divided by coefficient of the incoming variable for the x2 row as well as the x3 row. First, we have to look for the x2 row. In the x2 row, xb value is the 1 and coefficient of incoming variable is minus 4 by 3. If any coefficient is the negative value or 0, we have to neglect that one. So here we are not calculating the minimum ratio for xb divided by coefficient of incoming variable for the x2 row. So next we have to calculate the minimum ratio, that is xb divided by coefficient of incoming variable for the second row, that is the x3 row. Here xb value is the 11 by 6 and coefficient value is the 11 by 9. So 11 by 6 divided by 11 by 9, its value is the 9 by 6, that is the 1.5. So minimum ratio is the 1.5 for the x3 row. So x3 row we are calling as the key row and x3 variable we are calling as the outgoing variable. Next, we have to identify the common element in the key row as well as the key column. Here key row is the x3 row and key column is the x1 variable column. So among these two, key column and the key row, common element is the 11 by 9. This 11 by 9 we are calling as the key element. Next, we have to construct the new simplex table by entering the incoming variable. Next, to construct the new simplex table by reference of old simplex table. Here x3 variable is leaving the basis and x1 variable is enter into the basis. So modify the basis by replacing x3 with x1 in the new simplex table and its CB value is the -4. Next we have to modify the remaining values by the following row operations. That is, first row operation is R2 new equal to R2 old divided by 11 by 9. Here 11 by 9 is the key element. And the second row operation is R1 new equal to R1 old plus 4 by 3 into R2 new. So first we have to look for the first row operation, that is R2 old divided by 11 by 9. First we have to write down the R2 old elements, that is 11 by 6, 11 by 9, 0, 1, 1 by 18, minus 2 by 9. Then R2 old divided by 11 by 9, that is R2 old into 9 by 11. So 11 by 6 into 9 by 11, it is become the 3 by 2. Then 11 by 9 into 9 by 11, it is the 1. 0 into 9 by 11, it is the 0. Then 1 into 9 by 11, it is the 9 by 11. Then 1 by 18 into 9 by 11, it is the 1 by 22. And minus 2 by 9 into 9 by 11, it is the minus 2 by 11. So enter these values, these R2 new values in the second row of the new simplex table. So next we have to look for the another row operation, that is R1 new equal to R1 old plus 4 by 3 into R2 new. First we have to write down the R1 old elements, that is 1, minus 4 by 3, 1, 0, minus 1 by 3 and 1 by 3. Next we have to write down the, R2 old, R2 new. R2 new elements are the 3 by 2, 1, 0, 9 by 11, 1 by 22, minus 2 by 11. Next we have to multiply this R2 new elements with the 4 by 3. Then these values will become the 3 by 2 into 4 by 3, it is the 2. Next 1 into 4 by 3, 4 by 3, 0 into 4 by 3, 0, 9 by 11 into 4 by 3, 12 by 11, 1 by 22 into 4 by 3, it is the 2 by 33, minus 2 by 11 into 4 by 3, it is the minus 8 divided by 33. So next we have to do the operation for the R1 new, that is R1 old plus 4 by 3 into R2 new, that is 1 plus 2, that is the 3. Next minus 4 by 3 plus 4 by 3, it is the 0. 1 plus 0, that is the 1, and 0 plus 12 by 11, it is the 12 by 11. Next to minus 1 by 3 plus 2 by 33, it is the minus 3 by 11. Next 1 by 3 plus 1 by 3 minus 8 by 33, it is the minus 1 by 11. Next we have to calculate the Zj minus Cj values and check the basic feasible solution for optimality. So first we have to calculate the Z1 minus C1, it is the minus 3 into 0 plus minus 4 into 1 minus of minus 4, it is the 0. Next Z2 minus C2 is the minus 3 into 1 plus minus 4 into 0 minus of minus 3, it is the 0. Next Z3 minus C3 is the minus 3 into 12 by 11 plus minus 4 into 9 by 11 minus of minus 9, it is the 27 by 11. So next Z4 minus C4, it is the minus 3 into 3 by 11 plus minus 4 into 1 by 22 minus 0, this value is the 14 by 22. Next Z5 minus C5 will become the minus 3 into minus 1 by 11 minus 4 into minus 2 by 11 minus 0, it is the 1. So here Zj minus Cj values are the 0, 0, 27 by 11, 14 by 22 and 1. So here observe all the Zj minus Cj values are the greater than or equal to the 0. Then we obtain the optimum basic solution. So since all Zj minus Cj values are greater than or equal to 0, Then current solution we are calling as the optimal basic feasible solution. So at the optimal basic feasible solution, in the basis x1 and x3 are having, so x1 value is the 3 by 2 and x2 value is the 3, and in the basis there is no x3, so x3 value is the 0. Then substitute these x1 and x2, x3 values in the original objective function, that is maximum z equal to minus 4x1, minus 3x2, minus 9x3. Then maximum z equal to the minus 15. So this is the solution, and thank you.